Recall that we could use a 2's complement to perform a binary subtraction. Now suppose we wanted to subtract 7 here from itself, then that's the same thing as adding the 2's complement, and the 2's complement is basically just flipping those bits and adding 1. So what we get is 1, 0, 0, 1. So this subtraction is the same as adding 1, 0, 0, 1, and then we drop the leading bit. But in computer memory, you'll get an overflow, as we'll see, and that leading bit is dropped automatically. So for example, if we add the number to its 2's complement as follows, we obtain 1 plus 1 is 2, carry the 1, and we get 2, carry the 1, 2, carry the 1, and then we get 1, 0. But suppose we have a location in computer memory that contains 4 bits that are signed. So in this case, this operation causes an overflow, and this bit is dropped automatically. So where we have 4 bits signed, the first bit represents a sign of a number where 0 is positive and 1 indicates a negative number. And then the remaining 3 bits over here are used to store the actual number. So in our case where we have positive 7, we have 0 for the sign, and then 1, 1, 1 for the number. And now using this nibble, which is 4 bits, we can represent the following numbers in memory. So we have 0, 1, 2, and so on. So what we've done is represent the numbers from 0 to 7. And now to represent the negative numbers, we take the 2's complement of each of these numbers. So for negative 1, we flip the bits to get the 1's complement, and adding 1 gives the 2's complement. So that would be 1, 1, 1, 1 in binary, which represents negative 1. And let's do another example. So to represent negative 2, we flip the bits and add 1, which gives 2, and then we have 1, 1, 1. So minus 2 is represented as 1, 1, 1, 0. And if you continue this process, we have minus 3 up to minus 7. And to verify that these are correct, we'll start off with 0. So if we take the 1's complement and add 1, we get 0, carry the 1, 0, carry the 1, 0, carry the 1, and then 1, 0. And as you can see, because we only have 4 bits, the leading bit gets dropped automatically. So the 2's complement of 0 is 0, and if we add this to 0, you can clearly see that we get 0. Now similarly for 3, if we take the 2's complement, we flip the bits and add 1, so we get 1, 1, 0, 1. And if you add this to 3, we expect to get 0. So we have 0, carry the 1, 0, carry the 1, 0, carry the 1, and 1, 0. And we only have 4 bits to store the number, so this leading bit is automatically dropped. Now the negative numbers follow this pattern because they're basically minus 8 plus the number that's represented by the trailing 3 bits, and not the negative sign. So for example, here we have minus 8 plus 7, which is minus 1, minus 8, plus this number, which is 6, so that gives minus 2, and so on. So recall that 8 in binary is 1, 0, 0, 0. So if we flip the bits, we get 0, 1, 1, 1, and add 1 to obtain a 2's complement. So we have 0, 1, 0, 1, 0, 1, and 1. So the 2's complement of 8 is the same binary number. So negative 8 is 1, 0, 0, 0. So therefore 4 signed bits can represent the numbers from negative 8 to positive 7 in computer memory. Please subscribe, like and comment to help me reach more students.